All right, so welcome back to the first module. Today we will basically dive into the modeling part, right? So this is our third week of the course, and so far I've given you an overview of what you can think of as a generalized systems theory. Just to make one point clear that we use ODEs and differential equations because they are very powerful in describing and in terms of describing the dynamical system. And we are interested in dynamics because we want to predict the future states. And within the context of this very general view, we honed in a little bit in the previous lecture on building systems and cyber physical energy systems, which buildings are an example of. And so we saw how heating, ventilation, and air conditioning system works. Today, we will attempt to actually start modeling the system, right? So we are now sort of looking at, we've defined the CPS domain for the first module in this principles of modeling for CPS. But now we'll start with the modeling part. And while doing this modeling, I'll point out which principles generally apply to any CPS rather than just energy. And so we've spent quite a lot of time on looking at state space modeling examples, mostly from mechanical and electrical sort of engineering. Today we will see what are the physics-based first principles that we use to model the thermal dynamics of this single zone to begin with. And then our goal, of course, is to have a state space model that can maybe predict the temperature of any building or any space inside a building. So we'll set that up in terms of first looking at not mechanical or engineering, but what are the elements of a thermal systems, and I'll sort of refresh and introduce some vocabulary for us to be on the same page. And then we'll sort of see what we learned from the functioning of a HVAC system and how we can incorporate that knowledge in terms of creating a mathematical model that you will use and train with real data to predict the evolution of temperature in a building, right? And that's what is called this RC model that I briefly showed you in the previous lecture. But the resistances and the capacitances of this network model are thermal in nature and not mechanical or electrical, right? So we left our discussion on HVAC systems at this point where essentially the whole idea of any heating, ventilation, and air conditioning system is to satisfy thermal comfort. But there are other modalities of humidity, pressure, and ventilation as well that we briefly touched upon. And the idea was that the user, has a say in this matter, that if you can agree on what a comfortable set point temperature is for a room, you set that into the thermostat. And people don't generally even agree on that. There's a big research focus on trying to analyze why people don't agree on a common thermostat setting. But let's say we do have some consensus-based mechanism that we've decided it's 74. Then the dampers and the reheat at a local level will control essentially the heat extracted from the zone, right? Or they're controlling the set points of the supply air temperature and the mass flow rate to get the heat out of that zone if we're talking about cooling. And so there's a constant mismatch between what we sense from the zone through the thermostat or the thermocouple sensor inside the thermostat. And the PID loop is going to look at that error in the mismatch and try to adjust the damping position or the reheat value based on how to minimize that error. So this is HVAC. Now let's jump into how do you actually describe this mathematically and start modeling the system, right? So if you know anything about me by now, you know I like to tell stories. So here's this story of earlier in the 19th century, right? It goes back to more than 100 years ago. The engineers at that time, they wanted to answer questions about how can we improve the efficiency of a steam engine. That was the big breakthrough back then. And so those questions were of the form, how hot does the fire ought to be for this to operate efficiently, and or even what liquid to use as the liquid which we are boiling to generate the steam. Is it just water? Is it some treated water or a mixture of water and alcohol, whatnot? Right, so these were very profound questions at the time, and it's through this problem of making a steam engine efficient that they started looking at the science of what we now know as thermodynamics. Okay, so terms such as heat flow or temperature and energy, they entered the scientific vocabulary because of these problems. And so to refresh that, I'm going to reintroduce these terms which are present in this thermodynamics vocabulary, and we'll sort of take a very quick review of what heat flow is, what is actually temperature, how is heat transferred, and those are the principles of physics or the elements of this first principle modeling that we will leverage to model something as complicated as a single room or multiple buildings. All right, so just to sort of refresh your memory, heat is nothing but a form of energy. I mean, everybody knows that, but I'm just making it clear. And so mostly, just like we are interested in the rate of change of a state of something for a general system, in reality, things are interesting not because we just describe things by their heat content, but how heat flows into and out of a system, right? So remember this mental map of what a system is. It has this boundary, and there's some inputs and outputs, and it can interact with its environment, which is not a system. So heat flow is nothing but the rate of transfer of heat. So it's just a derivative per unit time. It's measured in watts. This is what we are most familiar with. And then there's something called heat flux. Flux in general is when you define something per unit area, or you define some flow per unit area to be precise, that becomes flux. So the heat flow rate per meter square of any surface, I can call that quantity as flux, and we will often use the solar influx from the sun directly onto a wall, for instance, to predict the temperature of the wall. And in that context, you will see this in a bit, but sometimes that solar flux is called irradiance or solar irradiance. So this is well known. Maybe some other definitions that you may have seen but forgotten. The heat capacity of a substance is the amount of heat energy needed to raise the temperature of that substance by 1 degree Celsius. Okay, so think of this as the thermal mass, or the mass equivalent of this thermodynamics sort of view of the world, right? So we've seen that this notion of capacity is like inertia, right? Whether it's in the mechanical system or in the electrical system. In thermodynamics, you have heat capacity. So it's a property of a material. That's what heat capacity is. And so the heat capacity is clear what it is. It's the amount of heat required to raise the temperature by a degree Celsius. But this definition is very loose, right? So what is meant by how much material we are talking of? So just to standardize this notion of property of a material, we tend to define a specific heat capacity, or sometimes people just, for brevity, just call it specific heat, whereas the correct term is specific heat capacity. It's the same thing as the heat capacity, but we are now interested in standardizing that you have to raise the temperature by a degree Celsius, but of 1 kilogram of that substance. So it's very naturally derived from what a heat capacity is. So then you become independent from how much material you're talking about. Just take the specific heat capacity, and that will give us some indication of what is this thermal inertia or mass contained by this substance. Mass flow rate is, as the name suggests, is just the rate of change of mass per unit time. So whenever there's the notion of rate, it's usually with respect to time. Sometimes it could be with respect to other variables as well. So these are just definitions, but the most canonical or most widely used equation, and that's the equation we will repeatedly use in our modeling as well, is this heat transfer, what we call 101, the very basic equation of thermal heat transfer. And what essentially this equation is telling us is that if the temperature of a mass M1 of a substance with specific heat capacity Cp changes from T1 to T2, then the amount of energy that is required to do so is given by this relation, right? So heat energy is equal to mass times specific heat. So essentially, when you multiply mass and specific heat, you are getting the total thermal mass. So it's the total thermal mass times the temperature over which that heat was sort of given into the system or taken out of the system if T2 was less than T1. Right, so this is the basic equation that we will time and again come to, and you can think in terms of what we have studied before about systems, right? So we are looking at, so heat flow is equal to some mass flow rate times delta T. This is consistent with our knowledge of what thermal mass is, right? So heat flow is equal to some capacitance times the rate of change of temperature. And in the previous equation, the rate of change of temperature is just delta T, because we are looking at, say, a single unit of time. Okay, so this is consistent with what thermal mass is. So very explicitly, the heat flow, why do I say flow? Because I'm taking a derivative with respect to time, even though in the original equation there was no flow rate. So if I actually take the derivative of this equation, the left-hand side, which is total heat, becomes heat flow, simply put. And what this is saying is that heat flow, which is Q dot or H dot, is capacitance or the thermal mass of the volume of that material times the rate of change of temperature in that material. Okay, so this is the basic equation which will be the backbone of all our modeling when we talk about the thermal properties of this building. Right, so how does it equate to what HVAC system does? So you've seen this before, and I didn't go into too many details, but essentially a HVAC system is doing exactly this, right? So let's sort of interpret this equation now, which says that the heat flow into a system or out of a system, the directionality, by the way, when I say into or out, will depend upon this relationship with supply and return. Okay, so if you are sending in cool air and the return air has a high temperature, then this becomes negative. Supply minus return will be a negative quantity. So essentially means you are cooling. And that's why we can interpret that as the heat from the system rather than into the system. So anyways, that's just a side note. What is important is that the thermostat is eventually controlling the flow, heat flow into the zone. How does it do that? It either changes the supply temperature, Ts, or it changes the volume or the mass of the air being sent into the zone at that temperature. Right? So rho is the density, and density times rate of change of volume, which really what the damper is doing, is essentially the mass flow rate from our previous equation. And as I said that, by looking at the mass flow rate times the specific heat times the temperature, resulting temperature between the supply and return, you can essentially model. So this is your first sort of model of what a HVAC system does. With the simple view of the world, we can calculate the heat flow into a system or from a system using this equation right here. Any questions on this? Okay, so quite straightforward. And in this case, I didn't pay attention. The title said it's for heating, right? So we are assuming that supply air is higher than return air. That's when you heat a room. You're sending in hot air and you are receiving back air at a less temperature. That's what heating does. The sort of dual of this is cooling, which says it's the return air temperature is going to be more than the supply air, and that's when there is cooling in the system. Okay, so these are basic ways to talk about heat flows into and out of a system, but we haven't really yet defined what this system or a zone is. So let me show you a picture which will make it super clear on why I call a zone a system. So essentially, if you look at a system, it has to interact with its environment. And so what we say is that a zone is nothing but it may have a physical boundary, which are the walls and the surfaces of the zone. And the only thing that flows into and out of the system and interacts with the environment is heat flows. That's sort of the simplified picture of how rooms operate in a building. Right? Every room is its own system, and the only inputs and outputs from the system that interact with the environment are flows, heat flows. That's how the environment exerts its influence on the system, and that's how the system sort of exerts its influence on the environment. And so all these arrows, they will become more clear later, but I want to just, I've said this very in layman terms, that we are these hot water bottles and we are emitting heat, and so is all the equipment in the room. These are flows which are generating heat that will be sent outside of the zone through the HVAC system. But likewise, there's temperature outside, which is, I think, in the mid-80s today. So there's some heat flow which is coming from the outside into this system as well, besides just the forced air that we are pumping into every zone. So the whole idea of modeling comes from defining two things, right? First is defining what is this boundary, And this boundary is often called the envelope of a zone or a building. And the second thing is, what are these flows in and out of these boundaries? If you can mathematically describe these two things, we have a very good chance of modeling the zone and predicting its temperature. And actually, the remaining lecture today is just to tell you and convince you how do we go about doing those two things. Describing the properties of the building envelope and how do we capture these losses and heat gains. Right, so gains are heat flows into the zone, loss. This is not maybe standardized language, but this is how I talk. So I just put it up there so you know when I say loss and gain, what does that mean? And another sort of tangential point is, in this building thermal modeling community, there are different types of gains, right? So gain is when heat flows in, but it could also be of many different types. What do I mean by that? So one type of gain is called sensible gain, or sensible cooling, sensible heating. And essentially, the name sensible is getting derived from the fact that anything which directly influences the zone air temperature. And now, we are not talking in general systems terms. We are talking specifically for a building zone. So anything which can directly influence the zone air temperature is called sensible gain or sensible cooling, because we can immediately sense it, right? There's no sort of delay in terms of the temperature increasing and you feeling that it's becoming hotter or warmer or cooler. And so what is not something which is not a sensible gain? It's not called nonsense gain. This is just called latent gain. Okay, so latent gain or latent cooling is indirectly you may feel it as a discomfort, but mostly you can think of it as things like humidity changes. So when I'm speaking, and even when you all are even breathing, we are exhaling water vapor into this zone air, which is changing the moisture content of this air. And eventually that will also dictate thermal comfort, or we can write an equation for that part of the HVAC component as well. But we will not look at latent gains for the most part in this course, because I want you to take away the main principles and not just become, this shouldn't turn into a building thermal dynamics class. So we'll mostly look at just sensible gains to keep things simple, and essentially we'll look at these flows which influence these sensible gains. What are these heat flows going through? This is sort of obvious, but it also helps to state this explicitly. Heat is flowing through all possible surfaces, right? So every wall, every ceiling, every floor of this room is conducting heat. The air inside this room is also having a heat exchange with every surface through something called convection, and I'll again describe these terms in more detail. There's internal heat gains that we are generating because of our metabolic activities. This computer is generating heat. These lights are generating. The projector is probably generating the most heat out of all equipment in this room. So all of these accumulated mechanisms are responsible for the generation of these energy or heat flows, and they occur through different mechanisms of heat transfer based on what we are talking about. Are we talking about the heat flow through a surface or a sort of a wall, or are we talking about heat flow through a fluid or the zone air or a gas? So this is again going back to maybe high school. Heat generally is known. The mechanisms of this heat transfer are conduction, convection, and radiation. Visually, this helps to know what this is. Conduction is because of heat transfer through physical contact. Convection is when the matter itself carries heat from one place to another. That's convection, and that generally happens in fluids. And radiation is the heat transfer through electromagnetism. Okay, so if we can describe the mechanisms of this heat generation and transfer, essentially we are answering that question of describing the properties of the building envelope and the heat flows. So for the next couple of slides, it's again going to become like a lecture on thermal dynamics for maybe 10 minutes at most. We are not going to go into super detail. Only we'll take away what's relevant to model this temperature of a building itself. Okay, so let's begin with conduction. And as I said, conduction is nothing but heat through a contact, physical contact, or heat through a substance, or transfer of heat from one hot part of a substance to a cold part. So that's still very loose, notion of what conduction is. Essentially, what is happening is when something is at a high temperature, and it will help if you think of this as a solid substance to begin with, the molecules within that substance are agitated because you are giving it a lot of thermal energy. In fact, you may not think about temperature in this way, but temperature is nothing but our estimate of the average kinetic energy of molecules in a body. Okay? So temperature is actually velocity in some sense of how fast things are moving about, or what we think how fast things are. So when things are agitated at high temperatures, there's a lot of collisions with the neighbors who are not yet agitated. And so on average, everybody wants to be equally agitated. There's this mismatch of vibrations of molecules. That's what conduction is. That's where conduction is stemming out from. What we observe is that if you have a substance or a mass of body and different parts of that substance are at different temperatures, there's going to be a heat flow from the hotter temperature to the colder temperature. And that phenomena is called conduction. In fact, we sort of oversimplify conduction. In reality, this is a very complicated physical heat transfer mechanism. Right? So for a 3D volume, or even for a real wall, conduction is in 3 axes. It's not just along one dimension. Right? So there is heat through a wall. So this wall behind me has some depth, and heat is coming or flowing either this direction or out towards you. But this wall also has an area, and there may be a temperature gradient in this XY plane as well, besides just this Z-axis flow. So in reality, if you have to model how the temperature is distributed on a surface, it's not easy. In fact, if you look closely at this equation which governs this generalized heat transfer through conduction, this is not even an ODE. This is a partial differential equation because we are taking derivatives with respect to x, y, and z. This is not a first order ODE as well because we are taking second order derivatives. So this actually breaks everything we've learned so far. So we will not use this. What we will use is an approximation. So we make assumptions that really what we want to know is what's the heat flow from the outside of my boundary to the inside. So I maybe really don't care how temperature is distributed in this 2D surface. I'm going to assume and simplify that equation in this following form, that the heat flow due to conduction is some property of the system times the temperature change through some depth of the wall or through some length of that material. Okay, so heat flow is K, which is called conductivity of a system. It's a new property of some substance, times the cross-sectional area into delta T, which is the temperature difference across which conduction is happening, and this is per unit length. So we divide by the depth of this mass as well. Okay, so this is the same equation as before actually. So Q is equal to some property times delta T. So A is the cross-sectional area, TH is the temperature, low temperature, L is the thickness. So just so that you visually also see this is I think a simulation where on the bottom you have different materials. We have 4 different materials: steel, ABS is like automotive grade plastic or acrylic, copper is a very good conductor, and then there is lead. And so the top surface of this, each of these columns have the same width, the same depth, the same cross-sectional area, everything. They have the same input, which is this top boundary of 700 something Kelvin. And so you can see that conductivity is actually trying to capture the property of the material on how well it conducts. Okay, so from our point of view, when we have to model and use conduction, it will occur through the following picture. Okay, this is what we care about when we model a building. So let's say there is a wall in a room, and on the other side of the wall, the temperature of the air is T outside, or T naught. And the temperature on the inside surface of the wall is T inside. In fact, to simplify things, forget about the air part I just said. You can simply say that the outside surface temperature of the wall is T outside, and the inside surface temperature of the wall is T inside. So already we are simplifying things, because really T inside is a distribution of its own. But we are saying that you can say the average temperature of the inside surface of the wall is by a single point measurement. And the same is for the outside surface. This wall itself has a depth L and a cross-section area of width by height. And so essentially what conduction, if we have to describe the heat flow through this wall, it will be given by that equation, right? So Q dot is conductivity times the cross-section into delta T divided by the depth or the length. Okay, so this is the same equation as before, simplified by making this assumption that we only care about the linear heat flow and not this cross-sectional heat flow. So I can rearrange some of these terms and rewrite this equation as the heat flow through the wall is delta T times, I define this new term called RW, where RW will be this quantity, because it's just, variables manipulation at this point. But there's a reason why I define this term RW is because I claim that you can interpret this quantity, which is a function of both the geometry of the wall and the thermal property of the material of the wall, as the resistance of the wall, the resistance through conduction of the wall. So can anyone give me a reason why this claim is correct from what we have studied before? Yeah.
It's kind of like in running where if you're trying to measure the resistivity of a wire, you have to account for the length, area, and then also the material property itself.
Okay, so the response was that it looks a lot like the resistance is acting like the resistance in electrical circuit, which is correct. But what I want you to encourage or open your thinking is why electric circuits, right? Why not like mechanical resistances? They're all the same, is what we spent some time on. So previously, when we studied generalized systems theory, we defined, this V equals IR, the classic Ohm's law. We define R, like I could have defined R as Ka by L as well, because it was like a free choice. But I chose to define it in the denominator because a generalized resistance is something which relates an across variable to a through variable through this relation. Right? So in our example, temperature across a wall is resistance times the heat flow through the wall. And it's because of this reason we define resistance in the manner of L over Ka. Is that clear? So then this becomes quite straightforward, that we have the heat flow times resistance is equal to delta T. So this can be represented using this electrical circuit that we've already seen many examples of this in terms of springs and circuits. Okay, where just for completeness, I'll say this one time, temperature is acting like voltage, and the rate of change of heat, which is heat flow, is acting like the rate of change of charge, which is current. Okay. So this is really what it boils down to, right? We will use time and again this equation to describe heat flow through a single surface, right? Right now, you can think of this wall, it just exists in isolation. We don't really know whether there's air on one side or not. We can describe the heat flow through the wall through conduction, right? So the key part is this is how conduction is defined with this notion of resistance. Okay, this is the same point. So now, we can push this idea even further. Let me show you. So this is on the right-hand side, you see the cross-section of a real wall. So there's a brick layer, then there's seems to be like a wood layer or, some kind of MDF sort of wood. Then there's some insulator layer, and then there's another brick or concrete layer. So it's 4 layers which are making up this wall, and this is what is described as a composite wall. Many people don't realize, but almost all walls are composite, right? They don't have the same layers, but they usually have more than one layer. And so then the question is, how do we model the thermal resistance of this wall? Well, you can now use any property of resistance, right? What we've learned is, we know that resistances add directly in series and in reciprocal when they are in parallel. So the thing is that in this thought experiment, the middle layer is green and orange, right? So it's a composite of two layers, and then there's a blue layer and a red layer. So I again claim that I'm going to treat, since I only look at this, one directional flow, I'm almost going to treat this wall as a stack of these three layers, RGB, and a stack of these three layers, blue, orange, and red. And for the top part, I'm going to have three resistances which are in series. And for the bottom part, I can have three resistances which are also in series, and then together they are in parallel. And so the boundary condition for the circuit would be T outside and T inside. But this, I'm claiming, can model the cumulative resistance of this wall. Now my question is, can you think of another way to draw this electrical circuit which could still be sort of correct? Right? This is my way of thinking of the problem, that the upper half is modeled separately from the lower half. What could be another configuration of this circuit based on the layers of the wall shown in this picture?
The orange and the green layer are in contacts and are transferring heat between each other.
Well, let's say we are neglecting any sort of y-dimensional flows. Flow is always left to right in this picture. That's a good observation, but we don't want to deal with y-dimensional flows. What's another way to represent this as a electrical resistance circuit? Yeah? Say that again? Three parallel? What? Does everyone understand why why this is an accurate representation? Because R1, R2, R3 is essentially the sum of the resistance of the top half, where the half is arbitrarily defined by this boundary. And 4, 5, 6 is the model or the equivalent thermal resistance of this bottom portion. So I'm thinking heat is flowing here. That's the top branch. It flows through the bottom. That's the bottom branch. Together, they are in parallel. What's another way? Yeah.
Would R1 and R4 and R3 and R6 be equivalent in this model? Could you rewrite it like one resistor for the blue block and then it splits into two parallels?
Exactly, right? So another way to draw this circuit would be, let me just have one resistance for the blue, which splits into green and orange and then combines back into R. So then you could compute a different expression for the total equivalent resistance, where you would only have one component of that in parallel, and then the other, and together they would be in series with the inner and the outer layers. So already we are making decisions which are these modeling decisions. Okay, so in this picture you can compute the equivalent resistance of this entire wall using that expression, which is simply saying that this is the 1 over RT is equal to 1 over the top branch plus 1 over the bottom branch. But in the alternate version proposed, we could have, I don't have the diagram for this, but we could have a single resistance for the blue, which branches out into two parallel resistances for the green and orange and collapses into another resistance for the red part. So the key point, and this is probably the first principle that you're learning, is both are going to be correct. The thing is that in our model, they will manifest as some expression for the total resistance. And when we try to find the value of this RT based on real data, it will adjust itself based on the actual heat flow. So this is a modeling choice. Both are correct. There is no wrong or right or preferred version. Yes?
Intuitively now, would this method be more accurate than
No, that's the same. So I know it maybe is easier to visualize, but there's no metric on which one is better than the other. So don't think in terms of better. There's no accurate metric. Intuition is not something we can empirically measure. So if you feel this is more intuitive, then by all means this is correct. Yes?
maybe in terms of order or
very good observation again, right? So here we have to model 6 unknowns, whereas in the previous sort of or in the alternate view of this resistance, we would only need 4, 1 for blue, 1 for red, and one for each essentially layer. So that's a very good point, and we can revisit that when we talk about model order and parameter tuning. Okay, so this is all you need to know about conduction. Essentially, that equation Q dot equals delta T by R, where R is L over Ka, where K is the conductivity, and then you can compose these resistances to model whatever. The next mechanism of heat transfer is called convection. Simply put, the convection occurs between a surface, where we can define what a surface is in just a second, and a fluid. So unlike conduction, where it's the agitation of molecules which is literally colliding with other molecules of the substance and making this heat flow, in convection, the molecules themselves, they have this energy, and they physically are moving to a different location in the fluid to transfer heat, right? So very simply put, you all know that hot air rises. So if you start lighting a fire here, the air around it becomes hot, and that air, the molecules which are hot will physically rise up. They are not agitating every molecule up till the surface. They are moving about. So the convection occurs because of the motion of molecules within a fluid. And I say fluid, air is a fluid, and so are liquids. So fluids are not just limited to liquids, and usually the surface could also be another fluid or another solid as well. So I'll give you an example of a convection where the surface is a fluid rather than a solid. So let's assume the convection on the surface of the ocean. Okay, so there's air above it, and the temperature of the surface of the ocean is some temperature. So that temperature and the air above it are in a heat exchange through a mechanism called convection, not conduction, where the surface itself is of a liquid, not a solid. So usually when we simplify things, we forget there's these counter examples. Don't worry about natural and forced convection. What we want to emphasize is that in HVAC, I said this during the previous lecture as well, this is a forced air system. We are forcing air to encourage convection, to condition the air, rather than this naturally occurring convection. A naturally occurring convection is what happens, say, between the outside surface of a building and the temperature of the air outside. Right? So if it's 90 degrees outside and the wall is at 60 degrees, there's going to be a convective heat flow from the air to the wall. So how do we model this is what we care about the most. Well, we define this because we model this exactly with the same equation, that the heat flow is some coefficient times delta T, where in this case, again, this coefficient is both the property of the fluid. So H is the heat transfer coefficient of the fluid, and A is the cross-section of the surface where convection is taking place. Right? It doesn't make sense to define some depth here, because what is the depth of the air of this room or the depth of the air outside this building? So all what we need to define is the cross-section over which convection occurs and the property of the fluid through which it occurs. And I'm telling you right now that in this course, the fluid that we will always deal with is air. There's not going to be any special case. Okay, so it's the same format where you can interpret now the resistance as 1 over HA, the inverse of this, to match this generalized resistance definition. But it's the exact same mathematical equation as conduction. The only difference is this coefficient now has a property of the fluid and the area rather than the specific heat, rather than the conductivity and area and length. Okay, so both those things hold. And then the final piece is what you call radiation. This is perhaps the most complicated one, but I'll again throw these keywords to trigger those neurons that you have seen before. So there's something called black body radiation. So any surface which is above 0 degree Kelvin is emitting electromagnetic radiation because of the temperature content. In fact, if you recall, it's proportional to some temperature to the power 4, or that's why hot bodies emit a lot of these electromagnetic radiation. So heat gain through radiation can also be described. The heat flow through radiation is also some property times delta T, where now we are looking at some coefficient of radiation and the cross section of the surface where radiation is occurring. To visualize this, to give you an example, here are two forms of radiation which will appear as flows in our system. So there's this fusion reactor in the air, right, and in the sky, and it's constantly bombarding us with different kinds of radiation. And so some of it is reflected back from, say, a glass surface. Some of this is absorbed by the surface itself, and then some is transmitted into the zone air. And so this cross-section area of the surface times some radiative constant of this glass will tell you how much of this energy flux on this glass surface is getting input as a heat flow into the zone, just using that simple equation. Another example which combines both conduction and radiation in this case is you have a wall. It's a composite wall with many layers. The outside air is, say, at 30 degrees. So there's going to be a convective heat flow between the outside air and the surface of the wall, because convection is between a fluid and a surface. However, the sun is also shining directly on this wall with some flux of delta times watts per meter square. So if we know the area of the wall, we can compute how much solar direct radiation also is going to lead to the temperature of this wall is going to change. And once this outside temperature changes, there's going to be conductive heat flow through the wall, which will change the inside surface temperature of the wall. Right? So the good news again is this is exactly the same as before. The only difference is that we are changing how we define our resistance based on how it appears in this equation of Q times the resistance equals delta T. The equation is the same for conduction, convection, and radiation. It's just the definition of the resistance which changes. Right? So try to just understand this property conceptually. Don't worry about these equations. This is not something you will get ever quizzed on. These slides are all online. The whole reason I prepared these slides is you can refer to them. You don't have to worry about, what is this HR and this epsilon. Epsilon, by the way, I think I didn't describe. This is another property called emissivity of a surface. So you can always go back and refer. Right? There's not going to be a closed book quiz in this course. What is important is you understand how we are using these principles. We actually just used one principle. That heat flow is some heat capacity times delta T. Then we described different properties of material, control, this relationship between heat flow and delta T. So questions on this before I move to the next half. All right, so now we are done. Okay, now for the remaining first module, I will not introduce any new definitions or principles again. Now we will just use what we have learned and create a mathematical model to predict the temperature of a single zone. We'll begin with a single zone, even though it may conceptually seem easy compared to this idea of demand response across multiple zones or even multiple buildings. This is the main example that we will use in this course, and then I will tie this back to this problem of demand response. Okay, so to model a single zone, what does it mean, right? So I want to take you back to the very first lecture where I said that all models are wrong, but some are useful. So today we will talk about what's a useful model for a single zone. Okay, so we want to predict, because we want to predict the future. I think everybody agrees on that. We can predict zone temperatures. We can predict humidity, because HVAC systems do more than just temperature. We can maybe predict electricity that this room is consuming, because for demand response, we care about electricity. We also care about thermal comfort. Or we can think in terms of energy and heat flow, the cooling load, the heating load of this zone itself. So it's the objective which defines how you go about designing your model. And this is the part which is the art of designing a model, right? It's not the science yet. Once you know what kind of model you want, you can make very sound decisions of model structure, so on and so forth. But there is no oracle which will tell you which model do you need. That is defined by a problem in that domain. So for the purposes of this module, we will pick the very first one. It's the most straightforward one. And actually, we have already seen that if you can predict the zone temperature, you can indirectly also infer the loads, the heating and cooling load of the space itself. So they're not independent. There's a lot of coupling between all these objectives. So let's say that's our goal. We want to predict the zone temperature of a single zone in a building. So to do that, we can either start modeling all the HVAC side of the building. You know, what is the VAV, what's the supplier temperature, what's the fan doing. I showed you that dashboard from UVA. We already have that information. Why don't we try to model all of that using physics? Or we can just abstract all of that out by saying that the HVAC system will send some heat flow into the zone at the end of the day. That's what we have already seen happens. So let me just model what we call the building envelope. Let me just model the boundary of this zone, the surfaces of this zone, all the walls, the floor, the ceiling of the zone, and the heat generation by the occupants of the zone. If I can model that or describe that, then I can just abstract the HVAC system out. So we are already making our model choices. We want a zone temperature prediction model, and we want to capture the properties of the building envelope. So how do we do that? How do we do the building envelope part now? Well, we need properties of the material of construction of this zone. Why do we need that, and what kind of properties? Like, maybe I don't care about the electrical properties of the wall. I need to know all those different coefficients that appeared in my conduction, convection, radiation equations. I need to know what is the equivalent thermal resistance of a composite layer in every wall. Therefore, I need to know what material they are made up of. I need to know their geometry. All these coefficients, the resistances, they are a function of the material property and the geometry. So I need to know many, many surface areas of walls, their thickness, the volume of the air inside the zone. This is all information I need to know in order to apply these principles of thermal modeling that we've learned. I need to know the operation, right? I need to know when is this room occupied so that I can model. There's 30 people right now, 30 people multiplied by the average metabolic rate of a human being who's sitting, multiplied by the average heat emitted by that person. That's my internal occupancy heat gain. I need to know when the lights are on, because lights are heat generators. I need to know when the projector is on. So I need to know operational details, but I'm not going to model these equipments. I'm not going to go and model how much heat this light bulb is emitting. I can just sort of take a guess over there. So I need to know this is what is called the building information modeling part, because you need to know the design and the materials and the operation of the space you are trying to model. We are going to model the envelope of that space. That will become clear in just a second. And we want to predict zone air temperature. So finally, what are these different surfaces that we want to model? I think we have gone over this, but let me define them. In a single zone, you have something called an external surface. So external surface is anything which is the outside condition for that surface is the ambient temperature outside. Right, so actually this zone doesn't have any external surface because we are in the basement and none of these walls are exposed to the outside air. But we could still model an external surface in a zone which has one. Then we need to model the ceiling, right? So in our case, the ceiling is being driven by the temperature of the floor above us. Okay, that's the boundary condition for the ceiling. The boundary condition, likewise, for the floor is maybe the ground temperature of this building. And we can use that as the boundary condition to drive our conduction model for each of these surfaces. And then for a surface such as the one on the left or behind you, the outside condition is other zones. So those are called internal walls. Internal walls are different from external walls simply based on their boundary condition outside. What is the temperature outside? It's another zone. If the temperature outside is the actual ambient temperature, then that's an external wall. And finally, we do have some different materials. So there are breaks in this wall in terms of the windows and doors. We model them as separate conduction channels or convection channels. Okay, so it seems like it's going to be a lot of work based on this picture. And it is significant work, but you will see in the next 10 minutes how a single equation that we have seen will make this super easy. We will use the same canonical piece time and again to model each effective branch of how this zone interacts with its environment outside. Talking about heat gains itself, so far we have seen geometry, materials, operation, surfaces. We also need to account for different heat gains which influence the temperature of the air in this zone. So we've already seen some examples like solar irradiance. So if there is an external wall in the zone, chances are it's getting flux from the sun. So we account for that direct heat gain. The same can be true for ceilings, right? If we were on the top floor of the building, we would have direct heat gain on the ceiling. Then there's heat directly transmitted through windows. We've seen examples of that as well. The radiation can come in through the windows. Not only that, windows can also act like a thermal conductor between outside and inside temperatures. Total internal heat gain, right? So not only the humans, but every surface of this room, the furniture, then the chairs and everything, every equipment here is also emitting radiative heat because of this black body radiation phenomenon. So if we want, we could really, have this OCD of modeling every single piece, but you will see again, one of the principles that we will learn is how do you abstract things out and keep them at a level which is a good trade-off in, say, the number of parameters, something which was brought on earlier, and also the effort that it requires you to build a model. And you will understand that later. But for now, let's try to have an exhaustive list. So I can keep going. You can have different heat gains with other zones. We want to definitely model what the HVAC is doing in the system, how much is the effective cooling or heating load of this zone. And then we also want to model the boundary conditions for everything, right? So what's the outside surface temperature of this wall? So it's a lot of information, and I'm not denying that, but you will see there are several tricks that we will use to make it much easier to go and model any building or any zone after you have gone through this exercise. So while we are on the topic of heat gains, I have said this many times, everything is emitting heat. I'll also specify this, right? So when we emit heat, we as in the occupant or equipment, we also emit two different types of heat, right? So like my body and your body is a surface. So there is convection between the surface area of your body and the air in this room, because maybe my skin temperature is different from the zone temperature, and there has to be convection. But I'm also this at a positive temperature, so I'm emitting radiative heat gain as well. So is everything else, and so are you. So when I say, humans are these hot water bottles, this is what I mean. We are these hot water bottles which are moving about in the system, generating these internal heat gains by convection and radiation. Conduction is probably occurring on my arm between the molecules of my skin itself, but it's not really influencing the zone temperature. Okay, and if you're still not clear, then this picture shows you what is happening, right? So this is not a picture of heat flow. We can't visualize heat flow, or at least I don't think so. This is a picture of temperature in a typical office building. So you can see that there would be conduction on the surfaces or the furniture or even the body of a single human being. But what we are interested in is the radiative gain and the convective heat gain. So all internal heat gains, the take-home messages, they will be split into some radiative part and some convective part when we try to account for them in our model. So I've been referring to this model for quite a long time. So let me get to actually one piece, and that's the last thing we'll discuss today, on how do you model the heat flow through a wall, a single wall, by using these conductive convective principles that we have learned. And that will become the key piece, because all surfaces are sort of walls. The floor and ceiling are also walls, right? Conceptually, it doesn't matter if they're horizontal or not. So it's just heat transfer through the wall, and if we can describe it with a mathematical model, we have a good shot of modeling all the surfaces of this room. And the reason we want to model the surfaces is because we want to then associate flows of how heat flows outside the surface and into the zone through the surface. So here's a picture to clarify something. So let's assume this is an external wall which is exposed to direct radiation from sunlight. And this could be on many forms. Don't get confused between long wave and short wave, but since this is here, I feel it's my duty to explain what that is. So short wave can be thought of as ultraviolet direct radiation onto the surface, and long wave is that sunlight can get reflected from everything else and from the ground and then come to the surface as well. So essentially the wavelength has increased, it becomes infrared. And also other outside buildings and trees and vehicles and all the environment outside is also emitting this radiative radiation, which is also getting absorbed by the wall, right? So we have direct irradiance on the outside surface of the wall, which is on this left plane. Then there is a convection exchange with the air molecules which are outside the building, right? So it's convection because it's a fluid and a surface, and there is some radiative gain. So because of these causal effects, the temperature of the surface is going to increase over time, over day, right? So at noon, this component is probably the highest, and then just after noon, the temperature is at its peak, around 2 p.m., 3 p.m. Okay, so this temperature increases. That causes a conduction through the wall now. The driving force for the conduction through the wall is this outside temperature on the outside surface. Then you can think of the other half of the wall. There's no literal half, I'm just abstracting it out, where this conduction flow, which is going through the wall, is going to change the temperature of the inside surface of the wall. That change in temperature will have a convective heat transfer with the air inside the zone. So this wall, you can already, just by this verbal description, you can imagine this wall has some thermal mass, which is acting as this delay between the outside boundary conditions and how much time it will take for that to appear on the inside surface. But that's happening continuously 24/7, 365. That's not the only thing which changes the inside temperature. So, the conduction will change the inside temperature. The occupants are also emitting radiative energy, which we just saw. So there's a radiative exchange which is also getting absorbed by each and every surface of this room. So there's like a trigger from both sides which is governing the outside and inside temperature of the wall. But that's sort of the understanding that we need to have. So going to the actual model, and then I'll pause for some questions because this is new stuff now. Here is what I claim is one way to describe this phenomena that I just told you right now, okay? So this is my hypothetical wall, this sort of rectangle or almost a rectangle. I introduce, first of all, I say that the outside condition, boundary condition, is the temperature of the air outside or on the other side of the external wall. Then there is a convective heat transfer between that boundary condition and the outside surface of the wall, which I denote by this temperature T1. And the convective heat transfer is shown by this 1/HA resistor, right? Convection doesn't depend upon any length. It's just the convective heat coefficient times the area. Then I say that T1 is my interpretation, or I am saying that this can be thought of as a state of this model that T1 is going to be responsible for some conduction through the wall, where we have to assume that the inner surface of the wall is at temperature T2. And we can describe this conduction by a resistance, which is this conductive resistance, which is this property of L over K, the Ohm's law stuff that I talked about earlier. And finally, there's a piece where the inner temperature of this wall has another convective heat transfer with the zone temperature. So here I am explicitly ignoring the radiative heat gain that can also come to T2, because it's negligible compared to the main thing, which is convection. Whereas on the outside, there is this other part, which let me highlight. There's something called Q source, which is directly as a heat input to T1s. Can anyone guess what this could be modeling, what this term is for? Why do we have some direct heat gain at the outside surface of the wall? What could that be accounting for? Sunlight, right? The solar irradiance is different from convection. Convection is occurring between air and the surface of the wall. This is a direct heat flux on the outside surface. So we have almost like a new input, Q source. Okay, so this configuration has two interior nodes, which are T1 and T2. These are arbitrary design choices that I am making to describe the dynamics of the temperature evolution of this slab. And then there is convection on both sides, T0 and TZ. So in this picture, there are a lot of assumptions. Let me just make sure we are all good with the assumptions. Right? First, we are assuming that the temperature inside is well mixed. The air is well mixed. What does that mean? Right? So if I ask you, what is the temperature in this zone, how will you measure it? Because what you can measure at best is at some point in XYZ what the temperature is. The true temperature of the zone is actually the integral of the function of temperature, which varies over XYZ with the volume of this zone, which we can never measure, to be honest. Like, nobody does that, right? So we are also making that assumption that when we say that the zone is at temperature TZ, air is well mixed. This is not true in general, right? So here's a snapshot of how air flows in the zone. So obviously we know this is not true, but we are simplifying. Another assumption we've already said is that we are assuming all walls can be denoted by one temperature, T0, T1 and T2. That's also not true, right? Walls, the temperature varies on walls in real world. So these are all assumptions we are aware of, and this should take you back to a couple of weeks ago when we saw that all models have these assumptions. This is where those assumptions are creeping into our model. So yes, our model is wrong because we have modeling errors, we have observational errors, but we want a useful model. So we still go ahead and proceed. And that's what I meant by that statement. Okay, so if we go back to this picture, by the way, someone, when I offered this course the previous year, there was a EE student who said, why are these voltages or the equivalent resistances, capacitances floating in the air? This is just for convenience. You can draw the complete circuit, which is equivalent to this, but I don't want to confuse you unnecessarily. So this is just a quick point in case you were wondering the same thing. Right? We can draw the circuit where the temperatures are voltages, and this is the exact same circuit as before. So the final part of today, and then we'll break. Let's go back to this picture. Now I can write the equations for the rate of change of these temperatures T1 and T2. So this equation says that some heat capacity of the wall times the rate of change of T1 is the sum of all flows at T1, which is what? This is the convective heat flow because of this T0 and T1. This is the conductive heat flow across this resistor R, and then there's a direct heat flow flux into the zone. So this is the same equation of heat flow is thermal mass times rate of change of temperature applied to node T1. And I can do the same thing for T2. The rate of the thermal mass times T2, the rate of change of T2 is convection with the zone air, TZ, so this part, this branch here, times the conduction between T1 and T2. Good so far? where what is R? R is a property of the wall, which is L over Ka. But now here's the question for all the chips. Okay, so this wall has some thermal mass, which is what? It's the density. Let's say it's made up of a single material as well. So the resistance would be just the property of the material, conductivity, L over conductivity times area. But the thermal mass of this wall would be some density times volume times specific heat capacity, correct? So if there's one wall which has this one thermal mass, in this picture, I have broken down that thermal mass into half. Actually, I'm defining C as half of that mass. And then I applied half of that mass to T2 and half of that mass at T1. So here's the question. Why does it make sense to do this? There's a very good reason why you have to have two capacitors and you cannot have one capacitor. And the reason is you've already done that in your assignment. So let me see if you can associate dots. Does everyone understand the question? The question is the thermal mass, which is the property of this wall, can be computed just by rho times specific heat times the volume, the numerator. But intentionally, I have defined half of this at T1, half at T2. In fact, the name of this model is 3 resistance, 2 capacitor, 3R2C. So this is not something I'm arbitrarily defining. This is how we model a slab. My question is, why does it make sense to split this capacitance into half? What could be the reason? Think through. Okay, let me seed some points and guide your thinking. Okay. Sure, but there's a very sound reason, which is more than just a mathematical convenience. So here's what I want you to think or observe. How many states are there in this model? Can you name them? 4? Is T0 and Tz a state or a boundary condition or an input? So how many states are in this model? Let's answer that. Can you name them? Okay, so the response was that T1 and T2 are the states of this model. Does anyone disagree with that statement? So that statement is correct. Okay, T1, T2 is something we have introduced. T0 is the outside temperature. I don't control it. It's not the state of my zone. And the zone temperature could be a state, but in this picture, it's just a boundary condition for convection. In fact, you can see what the state is because the state variables are changing with these dynamical equations. So now, can someone think through of why we need 2 capacitors? Very good. Thank you. To describe the dynamics of a system, you need some number of states. How many states do you need? The same number as the number of independent energy storage elements in the system. If we don't have 2 capacitors, we cannot have 2 states. Since we want to model the temperature outside and inside, we need 2 separate energy storage elements. That's the reason for this mathematical ambiguity. So, in a real wall, based on the layers, they could be different as well. But if you only had 1 capacitor, you couldn't write the differential equations for 2 states because you need a capacitor times the rate of change of temperature equals to flow. So that's why we spent all that time looking at energy storage and whatnot to convince you that this is one thing to say it applies for a simplified mass damper spring system, but it applies everywhere. And that's the power of systems theory. That once you have solved something, you can just learn and do that to anything that can be described in the same framework. Okay? So that's the reason why we need 2 capacitors, and this model is called 3R2C. So the last picture, and then we'll pick up from this point again, is to just explicitly show you that Here is where convection occurs. This point and this point, they are supposed to be colored, but this projector doesn't have enough resolution. Here is where convection occurs in the equations of the dynamics. Those are the convection terms, right? For T1, the convection is between outside and T1, and for T2, it's between the zone air and T2. Then there is conduction through the wall, which appears where? It appears in these two terms, because both T1 and T2 are getting influenced by conduction through the wall. And finally, this wall has some thermal mass, which appears here in this equation. So just using a single equation and just looking at the properties of convection, conduction, and we are ignoring radiation besides, this term is sort of capturing the influence of radiation, we can describe the rate of change of temperature of a wall, provided we know all these properties of the R and the C. And so this is the building block. This 3R2C network is the building block of creating a network now where every branch could be 3R2C corresponding to every surface of the zone, and collectively will result in a state space model for the zone. Okay? So we are getting close to our aha moment where everything will fall into place and you'll see this state space model in all its glory. And we're also getting close to another assignment. Okay? So that's all for today. If you have any questions, let me know. Otherwise, we'll pick it up on Thursday.